Hello everybody, moving on, Module 15, page 491 in your textbook. We're going to cover the first half of Module 15. We're going to go all the way to example 15.3 in your textbook today. What are we covering in this module? We're going to give the definition of chemical equilibrium. We're going to learn about the equilibrium constant. How do you use this equilibrium constant to predict the progress of a reaction? We're going to learn about the Chaltier's principle, pressure and the Chaltier's principle, temperature and the Le Chaltier's principle, and then we're going to learn about acid-base equilibria, the pH scale, and acid rain. Basically, we're going to cover the first three today. Let's see. Page 491 in your textbook. Follow along. Chemical equilibrium. Let's look at this picture. Number one, A and B are your reactants. So you put them in the beaker. The reaction begins. You don't have any product yet. There's a high rate of collisions between the atoms or molecules of whatever your A and B reactants are. And then you start the reaction forward. It's high. The rate of reaction towards the product is high. You're producing product. After a while, after a little bit of time has gone on, there's less reactant A and B to collide with one another. So the collisions between the reactants decrease. But the rate of the forward reaction also decreases. Less collisions means less product being produced. You have to collide first before you can become a product. Okay. So when that happens, the reverse reaction, C and D, who are the product here, now start becoming A and B. You see this little arrow right here? This is called the forward arrow, and this is the reverse arrow. So it's still very strongly towards the products, this arrow. You're producing more product, then product becomes reactant again. But time progresses in this reaction. What happens? Well, the rate of forward reaction equal to the rate of the reverse reaction. You see the two arrows now are the same length. And when they are the same length, it just means that the rate of A and B becoming C and D is the same rate as C and D become A and B. This is called equilibrium. It's a dynamic equilibrium because both reactions are taking place. You have reactant A and B becoming product, C and D, but at the same time, C and D break down to become A and B. We have covered before that you never run out of reactants. There's always a tiny bit of the product breaking down into A and B. There's always a tiny bit of the reverse reaction going on. At the point of dynamic equilibrium, when you reach these, the concentrations stay constant. A, B, C, and D, those concentrations stay constant. Now, let's look at this from a different point of view. Page 492, figure 15.1. You have a picture like this. This is a reaction. Let me see if it matches the one you have. They don't tell you what you have in your picture, but in this case, the picture I put here, the graph I have here is hydrogen and iodine becoming hydrogen iodide. So when you start, you have high concentrations of your reactants. The reaction starts, and as time progresses, this is the reaction rate, as the reaction progresses forward, what happens to the concentrations of hydrogen and iodide? They start to decrease because you're creating product. Okay, as you create product, the concentration of the product increases. Here you go, you increase, and when that happens, the reverse reaction starts going that way. So your product now has become the reactant in the reverse reaction. becoming the hydrogen, breaking down to hydrogen and iodide. When it reaches this point, you have reached equilibrium. The rate in which your reactants become product is the same rate as your product becomes reactants. You see, the reaction rate now is level for both reactions. This is equilibrium. And you express equilibrium by the double arrows. Well, half arrows. Forward reaction, reverse reaction. Equilibrium, the forward and reverse reaction occur at the same rate. The value of this rate is the same for both reactions, the same value. Let me read this to you. Chemical equilibrium, you need to know the definition. It's the point at which both the forward and reverse reaction in a chemical equation have equal reaction rates. When this happens, the amounts of each substance in the chemical reaction will not change, despite the fact that both reactions still proceed. So the concentrations do not change when you reach equilibrium, because the amount of product that you're creating in the forward reaction matches the rate in which it becomes again from reactant. Sorry, this is the product, but it becomes a reactant here. In the reverse reaction, this becomes the reactant. So let's say that the product now becomes reactant. Okay, so the rates are the same, concentrations stay the same. Okay, you will do experiment 15.1 if you want at home as extra credit. It's kind of messy, you're gonna have to do it in the bathtub, but it's a good demonstration of equilibrium. So it's up to you. If you need extra credit, do it. If you are curious, do it. Let's look at equilibrium constants. K is going to be your equilibrium constant. Sometimes you have the K with EQ for equilibrium. Here's a reaction, a standard reaction. A and B become C and D is in equilibrium. You have the double arrow here going forward and reverse. And here you have concentrations. So brackets mean the same thing you had in the last module, means concentrations. But you have your products at the top, you have your reactants at the bottom, and your exponents now are your stoichiometric coefficients. So they become part of the equation. When you are calculating equilibrium constants, and you're going to see in a minute how we apply these to determining if a reaction has reached equilibrium, if it has not, if it's going to go towards the products, if it's going to go to the reactants, what's going on with that reaction. This helps us figure out what's going on with that reaction, this equilibrium constant. But when you are putting concentrations, you ignore solids and liquids. You only will be using the concentrations of gases and aqueous substances at equilibrium. And you have to be careful because sometimes the problems will give you information about when you start, these are the concentrations, and then we'll say, and these are the concentrations when you reach equilibrium. Well, when you do the problems, the concentration you need to use is the concentration of those reactants and products that are aqueous and gas at equilibrium. That's why it's called the equilibrium constant. So let's see. Why are we not taking into account the concentrations of solids and liquids? Well, the concentration of solids and liquids are essentially constant. You cannot measure concentrations of solids. Concentration is given in molality per liter or mole per kilogram of solvent. And solids must just have mass, not concentration, when they are not in a solution. He goes over these with you. This is like a summary of what he tells you. And you need to know why solids and liquids are not taken into account. Liquids the same as solids, okay? But he doesn't give you a lot of detail because this is the first year of chemistry. Just know that this is why. Mass instead of concentration for the solids and liquids. Let's look at an application. Page 496, example 15.1. The following reaction, you have nitrogen and oxygen, will give you nitrogen monoxide. Everything is a gas, great. You are at equilibrium. You see the arrows here, both going both ways. So they reach equilibrium when the concentrations are, and they give you the concentrations at equilibrium. Great. They are not trying to trick you here. What is the equilibrium constant for this reaction? And the second section says, a chemist is studying the following reaction. And the chemist starts with, they give you concentrations when it starts. So they are trying to trick you here. And he finds that the reaction reaches equilibrium when the concentrations reach. And they give you the value of concentrations at equilibrium. So what is the equilibrium constant for this reaction? Be careful when you read the problems. You will disregard any concentrations at the beginning. You only use concentrations at equilibrium to calculate the equilibrium constant. So let's go ahead and do this. Let me get my pen in white. Remember that the constant equals the concentration of your products this is the standard formula. Just want to write it down. Okay, so products at the top and reactants at the bottom. It's very important for you to remember this, okay? So you need to memorize how to put this together. So for the first section, who is a product? You have the nitrogen monoxide, and at equilibrium, we're going to look at the concentration in a minute, but you also need to notice that you need to put a 2 right here, exponent 2, because that's the stoichiometric coefficient that goes with the nitrogen monoxide. So your reactants go at the bottom, and who are your reactants? Well, you have your nitrogen, exponent 1, so we don't put anything, and you have your oxygen. And you also have a stoichiometric coefficient of 1, so you don't put anything. All these concentrations are at equilibrium, so we need to make sure that we put the right information in. In this case, they didn't give you anything to trick you. So plug it in, okay? What's the first concentration? We had 4.51 molarity to the second power divided by 0.354 molarity and 0.124 molarity. Now put everything in the calculator and you find that you have a value of 463 is your constant. That's a very big equilibrium constant. Being very large like this means that you had a lot of product at the top. This is dividing, so dividing means you're making a number that's smaller. Being very large, you have a lot of product being produced. That's what it means. But let's look at the units. This is m to the 2, but then you're dividing by 2 m's that are multiplying each other. So this right here doesn't have units. Okay. The equilibrium constant will have different units for different reactions. Just like the rate constant that we saw in the previous module. So be careful with the units. They change depending on what reaction you're working with. In this case, they cancel one another, so this one does not have units. But this is it. This is your answer. You leave it like that for right now. Let's look at the second section. Once again, remember to check to see that everybody is a gas or an aqueous solution and can participate in calculating the constant. Everybody here is a gas, so everybody will count. The constant will have the products at the top, so concentration of the products. Who are the products? I'm just directly going to put it in here with the stoichiometric coefficients as exponents. My water also is a product and it has a coefficient of 6, so that becomes the exponent. And my reactants go at the bottom. Who is a reactant? Well, my ammonia. to the 4th power, because that's the stoichiometric coefficient that goes with that reactant. And now my oxygen. Everybody participated here. And you need concentrations at equilibrium. Equilibrium is the key word here. So disregard any information that's not about equilibrium concentrations. Let's put the numbers in. Okay, equals 0.40 molarity to the 4 times 0.60 molarity to the 6 divided by 0.80 molarity to the 4 and 2.7 molarity to the 7. So put up all the numbers in the calculator with all the exponents and you get this number, this value, 2.8. And if you notice, you have, let's see, the molarities right here are going to be to the 10 power, and the molarities at the bottom are going to be to the 11 power. So it's going to be 1 divided by molarity. This one has units, so be very careful. Okay, the units change depending on what reaction you are computing with. All the information has to do with the exponents. So this completes the example. Now back to instruction. The meaning of this equilibrium constant. How do we use this value? We're on page 496. Let's look at this. When your constant, your equilibrium constant, is larger than 1, the products are favored and the equilibrium lies far to the right. Let's look at this. If this number is larger than 1, what does it mean to be larger than 1? It means that the top and the bottom are not the same. It means that there is a lot more product, or there's more product than reactants. So the reaction is shifting towards the product side, towards the right. If this equilibrium constant is greater than 10 to the 10, so the power of 10, it's really big, a lot more than 1. This is really, really big, or there's very small amounts of reactant here. We say that the reaction has gone to completion. Okay? Another name is a quantitative reaction. It means that this forward reaction is very, very strong. There's a tiny bit of product becoming reactant because you never get rid of all the reactant. There's always a tiny bit, but it's almost negligible. That's why it's called to completion. It's called a reaction to completion. Means most of it has become a reactant. I mean product. I'm sorry, I used the wrong word. Please excuse me. So when we say to completion, means you created as much product as you could. Almost all the reactant is gone. Okay, but just remember that it just means the top is really, really large. Now, the equilibrium constant being 1, what does that mean? The top and the bottom is the same. So the concentrations of the reactants and products are approximately equal. I mean, we're talking about 0.99 point whatever. You're very close to 1 and you can round it to 1. It's almost the same. The forward reaction and the reverse reaction reach a point in which the amounts are the same on both sides. That's what it means. What about the equilibrium constant being smaller than 1? What does that mean? If it's smaller than 1, it means that the bottom was larger than the top. Who is at the bottom? Your reactants. So this more reactant than product. That's what it means. The reactants are favored and the equilibrium lies far to the left. If this constant is greater than, value is greater than 10 to the minus 10, so it's a very small number, meaning this was extremely large, meaning the forward reaction did not produce a lot of product. We consider the reaction to be a non-reacting reaction. If you hardly produce any product, that reaction is not working. Okay? So you need to know this because you're going to apply it in a minute. You need to know what it means if a constant is bigger than 1, equal to 1, or less than 1, and how to apply it to reactions. What do I mean? Page 501, example 15.2. What is the equation used to calculate the equilibrium constant in the following reaction? And then what is the expression for the equilibrium constant for this reaction? So we're not yet applying what we just learned. It's just one extra step. Let's see. They want you to check solid, gas, gas, aqueous, liquid, and to remember to disregard any solids and liquids. So before we can start applying the constant, equilibrium constant, we need to make sure that you remember that they will not participate, solids and liquids will not participate when you're calculating the constant. So what do, oops, didn't mean to go here yet, I meant to go here. So what does that mean? So, example 15.2 on page 501, the constant has the concentration of the products at the top to the exponent here, whatever it is, divided by the concentrations of the reactants to whatever exponent it is down here. We're not going to write the whole equation because I'm lazy like that. And you need to disregard any solids and liquids. So let's put the products at the top. Who is the product here? Well, the ammonia and the hydrochloric acid. Both are gases, so they participate. Concentration of the ammonia to exponent 1, and hydrochloric acid is a gas, so participates to exponent 1. It should be divided by the concentrations of the reactants to the stoichiometric coefficient as an exponent. But here we have a solid. We're not going to include the solid, so you would stop right here. This is the equation that would allow you to calculate the equilibrium constant. So you would stop right here. For the second one, you need to do the same thing. So your constant is going to be the products that can participate. So you're going to disregard the water because that's a liquid, but you're going to include the concentration of this large molecule. It's an O. An oxygen to exponent 1 because that's the stoichiometric coefficient that accompanies this molecule. And let's look at the reactants. Aqueous and aqueous will participate, so great, we're going to include them both. Exponent 1, and here the second reactant also participates in the equation because it's aqueous. Okay, exponent 1 as well. And you would stop right here. That would be the equation you would use to calculate equilibrium constants. So please make sure that you remember to not include solids and liquids. Because now we're going to apply this knowledge to the second section of today's instruction. So how do we use this equilibrium constant to predict the progress of the reaction? Page 501 plus. If you know the value of the equilibrium constant for a reaction, you can predict if the reaction has or has not reached equilibrium yet. But you need to know the equilibrium constant, okay, for that reaction first. Then compare what you get to that equilibrium constant. If it hasn't reached equilibrium, it must either make more product or more reactant. So how does it shift? Is it going towards the product? Is it going to the reactant side to reach that equilibrium? How is it gonna go, that reaction? Which way to reach equilibrium? So if the constant, equilibrium constant, we calculate is the same as the equilibrium constant that they will give you, then the reaction is at equilibrium. If they match, okay, it's reached equilibrium. If the number we get is less than the equilibrium constant, the reaction needs to shift towards the products to reach equilibrium. It should make sense to you. In a minute, I'm going to show you this. If the number we get is greater than the equilibrium constant, the reaction needs to shift towards the reactants to reach equilibrium. Okay? So have this in mind as we do the problems. We're going to apply this and I'll show you what I mean. Page 502, example 15.3. This is the last example we do today. And then we're going to do extra practice problems 3 and 4 to make sure that you understand how to do these. There's going to be 2 sections. I think I'm going to break it before I read it. I'm going to just do the first one. They're long. And then the next one. Not long as in math long, but as in reading. Number 1. A chemist is studying the following reaction. Nitrogen, oxygen, nitrogen monoxide. Great. She knows that the equilibrium constant for this reaction at this temperature is 0.050. Great. Suppose she knows that the concentrations of each substance are as follows. So they give you the concentrations at that moment. Determine whether or not the reaction has reached equilibrium yet. If it has not, determine the direction it will shift in order to reach equilibrium. So what do we need to do? Well, we know that the constant at equilibrium, okay, they tell us what the amount is. Let me copy it. 0.050. This is the equilibrium constant. Okay. And then they say, has it reached equilibrium when we have these concentrations? Well, we're gonna check to see what the K at that moment is. So who is up? Let's look at see at the products and the reactants will participate. Everything is a gas, so everybody's going to participate in the equation. So products at the top. Who is a product? The nitrogen monoxide. Does it have a stoichiometric coefficient? Yes, it's a 2. So that's our exponent. And our reactants go at the bottom. So nitrogen, exponent 1, and oxygen, exponent 1. Let's put the values given to us. What are the values? Well, we have 0.020 molarity to the second power, and then we have 1.5 molarity and 1.3 molarity. Put everything in the calculator and you get 0.00021. Okay. Well, what does that mean? Well, this number is a lot smaller than this number. Okay. What does it mean that this number is smaller? It means that it has not reached equilibrium. If they don't match, it has not reached equilibrium. So the first question has been answered. You would say not equilibrium. Okay. Now they want to know. What is it? How is it going to shift to reach that equilibrium? How is going to reach equilibrium? If the number is smaller, what does it mean to be smaller? It means that the bottom is larger than it should be. The bottom is dividing. The bottom is making the value smaller. So if you want to reach equilibrium, you need to increase the value at the top or decrease the bottom, okay? Which is the same. If you decrease your reactants, you're increasing your product. So you need to increase your product. You need to increase your product or shift. Another word for it is shift to the product side to reach equilibrium. You would write this in words, okay? So make sure that you understand what's going on here. If your value is smaller than equilibrium, or what it should be at equilibrium, it just means that you have a lot of reactants still. And to reach that equilibrium, you need to decrease these. To decrease means it's the same as saying that you need to increase your product. If this doesn't make sense, please ask me questions. We're going to have a Zoom meeting on Friday, as usual, or you can email me. Let me erase this and let's go back to the second section. The same chemist studies the same reaction again under different concentrations. Suppose this time she measures the following concentrations and they give you new concentrations. Is the reaction at equilibrium under these new conditions? If not, how will the reaction need to shift in order to reach equilibrium? Okay, let's go back to the board. And remember, your equilibrium constant was 0.050. So everything needs to be compared to this value, okay? You need to calculate the new constant at the new concentrations. Maybe the temperature has changed, the pressure has changed, something has changed to give you a new reaction with new concentrations. So let's put the numbers in. The product went at the top, 1.00 molarity to the second. And the concentrations for the reactants now are 0.100 molarity multiplying as a multiplication, 0.200 molarity. If you do the math, it comes up to 50. So the new number is 50. What does that mean? That's an enormous number, okay? Much bigger than 1. That means that you have a lot of product and very small amounts of reactants. The reactants are dividing. The reactants are making numbers smaller by dividing. So if you're not getting a number that's small enough, this is bigger, meaning not equilibrium. Okay, this is not in equilibrium because they don't match. And then it means that you have a lot of reactant. So if you want to reach equilibrium, to do that, this reaction is going to have to shift towards the reactants. If you want to reach equilibrium, to make this number smaller, you need to increase what's dividing. And what is dividing? The reactants are dividing. By increasing the reactants, you're going to make this number smaller and finally reach equilibrium. I hope this makes sense. Okay, what I'm going to do is give you the answers for 3 and 4, and then if you get it right, just move on, you're done. And if you don't get it right, just check to see how I'm solving these. So let's erase. You're going to find them on page 583, and I said 3 and 4. So let me get those numbers for a minute. 3. Let's see. Let's read it first. It says a chemist is studying the following reaction, and they give you the reaction. He starts with different concentrations, and then at equilibrium there are different concentrations. What is the value of the equilibrium constant? So let's see. Your K should have come up to 2.3. So this is number 3. If you got this value, you got it right. If you didn't, you can try again or check to see how it's done. So basically this problem was trying to trick you, to give you 2 different sets of concentrations when you start and the ones at equilibrium. And you need to remember that you need to disregard any information at the start. To calculate K, you need concentrations at equilibrium. So you have equilibrium of your products at the top and concentrations of your reactants at the bottom. And it looks like this. If you remember, we don't have exponents here because all the coefficients are 1, so you can leave it alone. Then put the numbers in. 1.2, 1.2, 0.80, and 0.80. And these are your volumes at equilibrium. All this is at equilibrium. And if you put it in your calculator, you get that 2.3 value. And the molarity, the input molarity key here is molarity, 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 and they cancel one another. That's why you don't have any units. Okay? And what does it mean to be 2.3? Let's talk about this for a minute. This is bigger than 1. Being bigger than 1 means that your products right here, are larger than your reactants. So this is shifted towards the product side. Okay? Although they didn't ask you that, here you go. And number 4, let me read for a minute. What does it say? They give you a reaction, great. They give you the equilibrium constant. If the following concentrations are present, is this reaction at equilibrium? And how must it shift if it's not at equilibrium to reach that equilibrium? So let me look at this. So it was not at equilibrium. So number 4, first, not equilibrium, and to reach, it needed to shift towards the reactant side. Okay, so if you got this far, you're done. You got it right. If not, how? Well, let me erase these. We're doing 4. Okay, at equilibrium is given to you 4.41 divided by molarity. Okay, everything needs to be compared to this number. They give you the concentrations at that particular moment, so we need to find out what constant it has at that moment with those concentrations. Product at the top, here's the product, and the reactants at the bottom with the right exponents. Remember, these are molarity, so when you put the information in, so basically 0.560 molarity to the second power divided by 0.280 molarity to the second power, multiplying by 0.294 molarity to the second power. When you put everything in the calculator, you get a number like this, 13.61 divided molarity. Okay, this is molarity to the second, and here you have 2, 4. So let me see this. I'm sorry, there was a 1 here. This is wrong. Okay, so be careful. So 2 divided by 3, so you left with 1 molarity at the bottom. Okay, so this needs to be now compared to the original, what it needs to be. What do we notice? We notice that it's not the same. As soon as you notice it's not the same, you know that this is not equilibrium. Okay, you know it's in equilibrium if they match. If they don't match, not equilibrium. What else do you know? By being a number this large, being larger than 4.4, you know that this right here is larger than the bottom. Who is at the top? Those are your products. Okay, so if you want to make this number smaller, you need to increase your reactants, which are dividing. So it needs to shift to the reactant side to reach equilibrium. And this concludes the first section of Module 15. Read your textbook for this section, add to your notes if you need to, review examples if you need to, work through them on your own as you encounter them, correcting them as you go. Study for your conceptual quiz this week. There's 1 extra credit lab this week if you want to do it. And study for your test. And I'll see you Friday. Bye-bye.